Hi everyone, welcome back. In this video we're going to learn about quantum numbers and orbitals. Please pause the video at this point to read over the specific learning objectives that you'll be expected to know for this video. Let's start with the end in mind. Today we're going to talk about some things that frankly are pretty complicated. Stuff that unless you are a physicist studying quantum mechanics, it probably won't make a whole lot of sense to you why the things are the way that they are. And so we just have to kind of accept with a little bit of faith in the scientists that what they're saying is true, unless you want to go way in depth on this. So where we're going with this is that we're going to be looking at orbitals. We're going to be looking at essentially what are representations of where electrons could be. And an orbital describes the probability of finding an electron in an area around the nucleus. So in other words, this green blob tells us about where we might find the electrons. And it turns out that this is super important because the location of the electrons tells us information about the energy of the electrons. And that tells us about the reactivity of the electrons and the molecule within the molecule. And that's what chemistry is all about. So we're laying the foundation right now for understanding how things actually react. Okay, let's get now down into the weird quantum mechanics world. So we talked about in an earlier video that electromagnetic radiation can behave as both a wave and a particle. Well, it turns out that matter can do the exact same thing. In other words, everything, whether it's light or whether it's matter, is both a particle and a wave. And if that doesn't blow your mind, think of it like this. You have a wavelength. You can't see it. You'll never notice it, but you have one. You could diffract. You could flop up and down like the waves on a sea. You are a wave. And you just have to take our word on that, unless you want to go deep down into the depths of all of this. So they took particles, electrons, and they diffracted them, and they formed a diffraction pattern that is identical to what you would get if they were waves. People have done studies, and they saw that you can relate the wavelength to the mass, or to the mass and velocity. In other words, this is the momentum. Okay? But here's why it doesn't seem like we have waves. Because for macroscopic objects, our wavelength is so teeny tiny small because our mass is so ginormous and we're moving at such small speeds that you'll never notice those waves, the fact that we have waves. For example, if you take an average person that's walking, their wavelength is approximately 1 times 10 to the minus 35 meters, which, believe it or not, is on the order of magnitude of the smallest known things to man, as in the fibers of the universe are made up of things that are that small. So our wavelength is so small we can never actually measure it. We just have to theorize about it. It's only when the wavelength is approximately on the same scale as the size of the object that then things start to matter. So when electrons are in atoms, they behave as what we call a standing wave. And there are some great videos on YouTube that you can find of standing wave demonstrations. And essentially think of like two people holding a jump rope, and they're going, they're having it go up and down so fast that it looks like that there's no real movement on the ends. And so that's what a standing wave is. It's a wave that doesn't appear to move. Each location has a fixed amplitude. And we call these points where there was no amplitude, those are called nodes. And this is the whole point with why we care about electrons as being standing waves, is that there are areas where they cannot be. There are areas where electrons cannot be. And so if we think of electrons as orbiting a nucleus, we could have a circular standing wave. And there are areas where the electron cannot be. We call those, again, nodes. When we look at these pictures of orbitals, there are areas where the electron cannot be. And those are the nodes. Okay? And this is important. We'll see later down the road as we start to look at how things react. So, where are the electrons? Well, this is, again, we're getting into some weird stuff here. You don't need to know a lot of the details of this. I will point out to you what is most important. You want to be familiar with some of these terms, though. Matter waves are described using what's called a wave function. And the wave function is meaningless. It has no physical significance. Just think of it like a graph on a page. But if we take that wave function and we square it, then that actually tells us the probability of where we can find an electron. We also call that the electron density or probability density. So those images that we looked at down here, these orbitals, these are based on the wave function squared. Okay? This is where we can find electrons, and we call these orbitals. And this is distinct from what Bohr looked at in terms of orbits. Orbitals work for all types of elements, whereas orbits only worked for hydrogen atom. And so because of the work of many quantum chemists and physicists in the early 1900s, we now know that electrons are not spinning around the nucleus like this, but they're actually in what we call orbitals. And it tells us information about the electrons' locations and energies. It tells us what energy states are allowed, and it gives us a physical space where these electrons might be found. Or in other words, orbitals, they have shapes, and they have predictable shapes, and we can use that to understand where are the electrons. So there are rules that dictate where the electrons can be. And when you did your reading, you saw this equation. This is called the Schrödinger equation, and it looks really simple, but it's actually super complicated. This involves doing multivariable calculus in multiple dimensions, and we're not going to ask you to do it. Instead, what we want you to do is recognize that the solution to this equation is what we call the quantum numbers. So in other words, if you have an equation y equals mx plus b, or whatever, let me give you a different one. Let's say that you have 17 equals 3x minus 1. The solution to that is solving for x. In that same way, the quantum numbers are the solution to these equations. So let's talk about them. We have the principal quantum number. Let me erase this information here and rewrite it. These are the solutions. Think X to the equations above. We first have the principal quantum number, and this tells us information about the size and energy of the orbital. This is the same quantum number that we talked about when we were dealing with the Bohr model. It has integer values of 1, 2, 3, 4, etc., up to infinity. We then have an L quantum number. This is called the angular momentum quantum number, and this tells us the shape of the orbital. So if we look here at the n value, if we look at this designation, this gives us the n paired with an L. So in this case, n equals 1 and L equals S, essentially. When n changes, the size changes. When L changes, the shape changes. Okay? And L is an integer ranging from 0 to negative n minus 1. In other words, if n equals 7, L can be any number from 0, 1, 2, 3, 4, 5, 6. Okay? Now, the ones that we care most about are 0, 1, 2, and 3. These get the symbol S, P, D, and F. And so that's where these come from. We have S-shaped orbitals, P-shaped orbitals, and D-shaped orbitals, and then F-shaped orbitals. And these ones are really complicated. And so we're not going to ask that you know what they look like. Just that they exist and how to deal with them in terms of L and D and whatnot. Okay? We also then have the M sub L value. And we call this the magnetic quantum number. And this describes the orientation of the orbital, or in other words, what direction it's facing. So if we have a p orbital, sometimes we have them look like this. Looks kind of like a dumbbell. And if we put it on an axis, we can get it along the x, the y, or the z axis. And those then correspond to px, py, and pz designated orbitals. And that's what this magnetic quantum number, what it describes, whether we are in the x, the y, or the z plane. These are integer values ranging from negative L to positive L, and they include 0. So if we combine these rules, we're going to see what our possibilities are here. And we're going to look at this on the next page. So using those rules, you'll recognize that there's only some quantum numbers that are allowed. And if we have our first 3 shells, our n values represented, we know that L is equal to anything up to n minus 1. 0 up to n minus 1. And so if n equals 1, L equals 0. If n equals 2, then L could be 0 or 1. And if n equals 3, L could be 0, 1, or 2. Remember, our M sub L values, these range from negative L to positive L, and they include 0. And so if L equals 0, that ranging from negative 0 to positive 0 just gets us 0. If L equals 1, we can go from negative 1 to positive 1. Again, 0 for that, negative 1 to 1. And if L equals 2, then we can have from negative 2 to positive 2. Now, let's use some more terminology here. We said that n equals the shell. Well, if you combine n plus L, you get what we call the subshell. If you combine n plus L plus m sub L, we then talk about a specific orbital. So what's the subshell designation for an n equals 1? Well, if n equals 1, L equals 0, that's corresponding to a s orbital. So that's a 1s orbital. For n equals 2, L equals 0, that's a 2s. And then if n equals 2, L equals 1, that is a 2p orbital. Remember that for our L values, designations of 0, 1, 2, and 3 correspond to S, P, D, and F. So when we fill this in, we start to see some patterns. We see that there's always going to be an S-type orbital in a given shell. And then as we go up, we start to get the larger shells, and they can hold more orbitals. The number of orbitals within a subshell is equal to the number of, is based upon the m sub L designations. So using these values up above, we have one designation for a 1s orbital, so there's only one orbital. We have one designation for a 2s orbital, so there's only one. But we have three possible combinations for a 2s. We could have, or excuse me, a 2p. We could have 2px, 2py, and 2pz. And then this process repeats. We can have 5 different orbitals for a 3D, corresponding each to the 5 orbital or m sub L designations. How many subshells are there? That's just adding up the total number of subshells. So we have 1 subshell in the 1s, 2 in the 2s, and 3 in the 3s. The number of orbitals is simply the sum of the orbitals within a subshell. So there's 1 orbital in the 1s, there's 4 orbitals in the second shell, and there's 9 orbitals in the third shell. That's a lot to think about. You essentially would be expected to be able to work through the rules on your own and to come up with whether or not certain quantum numbers are allowed. I'm going to walk you through a practice problem, and then we're going to pause there within this video before moving on to the actual orbitals themselves. So let's try a problem. Are these quantum numbers allowed? The answer here is no. Why not? Because L cannot be larger than n minus 1. Okay, you try the next one. Are these allowed? No. L cannot be less than 0. The next one. Are these numbers allowed? Pause the video, try it on your own. The answer is no. N cannot be equal to 0. You could also say that it's not possible because L must be less than N. Are these allowed? The answer is no, and the reason is because m sub L value cannot be larger than L. Finally, can this one be allowed? Pause and try on your own. The answer here is yes. This one is allowed. It follows all the rules. N is a number that's greater than 0. L is less than N and is equal to an integer. And m sub L is somewhere between L, negative L, and L. All right, so that's it for this video. The next time we pick back up, we're going to be looking a little bit more at orbitals. We're looking at degenerate orbitals and then the shapes themselves. Thanks for watching and have a good day. Bye.